So last time we talked about propositional variables, and we defined in a formal way what and or and not mean. So we talked about conjunction. That's the same as and the notation is that upside down, looks like an upside down V. And we talked about disjunction. That's the same as or, and we write it like this. And we talked about negation. It's often just referred to as not. And we write it like this, although some older textbooks will use a tilde to indicate the negation instead of that little handlebar thing. By the way, in LaTeX, that's just /not. I know somebody was writing in LaTeX on Piazza. Let's see. So the very last thing we left off with was talking about, I did an example of a compound proposition and making a truth table to sort of analyze it. And somebody asked, I guess, just a little while ago about what happens when you have a lot of variables and the truth tables end up getting very large, right? So maybe let's just do a quick example just to warm up, make sure we're all talking about the same stuff. And then I can tell you something more general about that. So let's just do an example of, let's do this one, P and how about not Q or P? All right, so if we want to build the truth table for this, just like last time, we start by writing down the variables and all the possibilities for what truth values they could be assigned. So these could both be true, could have true, false, false, true, and both false. And then to begin the analysis, I usually look at the parts because it's hard to do it all at once. So I'll make a separate column for not Q or P, right? Which is just, let's see, it's just this part. Because I see that the kind of the big picture is that we have these two things anded together, right? We have these two conjuncts. So one of the conjuncts already appears over here. It's just P by itself. And the other conjunct I'm putting as its own column. You could break this down even a little bit further.
Can I ask a question?
Oh yeah, sure.
Aren't we supposed to carry over the parentheses as well,
yeah,
since
sorry,
the order of operations?
Before you even said that, or just while you were saying it, I saw that. Yeah, the parentheses certainly have to be there.
Okay.
So you could break this down even further and just do, right, just figure out what Q or P is. In fact, why don't we go ahead and do that? So Q or P, right, that's the inclusive or, so that means one or the other or both of those two things have to be true. And in this case, we're going to have true, 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 false, right? One or the other or both. And the negation of Q or P, right? Remember, negation just flips trues to falses and falses to trues. So we'll have false, 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 and true. And then finally, this is my first conjunct and this is my second conjunct. And the whole statement here is just 1 and 2, right? So I'm just doing that so I don't have to rewrite it. But does everybody see like how this notation is supposed to work? Yeah. I mean, that's not really formal notation, but it's just to save space. So 1 and 2, that means both columns have to have a true in them in order for this thing to be true. And what do you see? Are there any places where this is true? They're not, right? In this case, in this first row, both P is true, but the second part is false, right? So that's a false. And then true and false is false. False and false is false. And false and true is false. So this is always false. Oh, I must have accidentally erased that when I erased the highlighting. And if we think about this, I mean, we've just made this formal analysis and we see that this thing's always false. When something is always false by its very form, so no matter what statements you plug in for P and Q, these propositional variables here, this thing will always evaluate to false. And if you think about what it says, right, this says P is true and it's not the case that at least one of Q and P is true, right? So Q and P must both be false, right? So, right, it follows from that. We can't have P be true and at least one of P and Q be true, be false, right? So when something is always false, we call it a contradiction. So this is always false by its very form. So it takes a little practice to work through these truth tables, but it's really just like, you know, compared to, say, something you would do with functions in a pre-calculus class or something, this is like the equivalent of making a t-chart, right? Plugging in values and just checking to see what they evaluate to. And since that came up on Piazza, let's think about the size of a truth table. So for a proposition with, say, n variables, right? So we've made propositions that have, we've made truth tables for propositions that just have one variable, right? Like the negation case, the number of possibilities for truth assignments to the variables that appeared in the truth table for the negation was just 2. If there's only one propositional variable, there's going to be 2 rows in that truth table because there's only 2 possibilities for truth value assignments to that variable. Most even of the examples that we've looked at are ones that have 2 propositional variables, a P and a Q. And when you have 2 propositional variables, there's 4 possible cases that happen, right? So that means those truth tables have 4 rows. I think last time we did one example with a proposition that had 3 propositional variables in it, and that had 8 rows. So I'm sure you see a pattern here, right? If we have a propositional statement with n variables, we're going to have 2 times. So this is, let's see, I'll write it like this: 2 to the 1. This is 2 to the 2. This is 2 to the 3. And in general, we'll have 2 to the n rows in a truth table for a statement that has n propositional variables. This is exponential growth in the size of the truth table. And that is bad news for us, right? Because if we get something like a statement that has just 5 propositional variables, we're already up to what, 16, 32 rows.
32.
Yeah, and that's just exhausting. You know, we don't want to write all that stuff out. So the wise thing might seem to be to write a program to do it, right? That would certainly take a lot less time than chugging through it yourself. But it's a very famous problem in theoretical computer science and mathematical logic, this problem called the P versus NP conjecture. And it is, I mean, we'll talk about that later in the semester, but it is very, very much coming from this exact phenomenon that if you want to know if it's possible to assign truth values to the variables of a statement in such a way that the statement will evaluate to true, that is a very difficult question to answer in a uniform way with a program, because the computation time grows to be so large, and that happens because the truth tables grow to be so large. So so we'll talk about that much later in the semester, but I'll just make a little note that the P versus NP conjecture is lurking here. Okay, so there's plenty of exercises to do on making truth tables and so on. So I think what somebody asked is there a shorter way to do this, right? There is sometimes, but it's not in a uniform way. And that is by using this algebra of propositions, which is going to lead us to the predicate calculus that we'll talk about later next week. Before we get into that, we have one more logical connective that we need to begin to understand, and that is the conditional statement. So we'll take two propositional variables, again, P and Q, and the notation is P arrow Q, right? So instead of the V or the wedge thing, we have P arrow Q. When we read this as P implies Q, or if P, then Q. And it seems so innocuous, but I just want to. I posted some additional documents on the readings page that I put up a little while ago on Canvas, and one of them is a part of a textbook written by Keith Devlin, and he introduces and or and not in much the same way that we have, although with a little bit, I don't know, kind of sometimes funnier exposition. So I encourage reading it. It's a good bit of it's a good book. But when he talks about implication, he just gives a really, really deep and worthwhile treatment of this, just important but very confusing, I think, connective. And he opens this section on implication with these two sentences. So this is section 2.3 in his book about implication. And he says, now things get really tricky. Brace yourself for several days of confusion until the ideas sort themselves out in your mind. So that would be my advice too. Brace yourselves, because although and or are very easy and absolutely consistent with the usual notions of and or that we use in our everyday language, that is not the case for implication. At least it doesn't feel like it initially. So when we think about something like if P, then Q, we are thinking of it as somehow, if P is true, that makes Q be true, right? So somehow this language, the way that we use it, entails causality, right? One thing causing another thing to be true, at least in our informal language. But in mathematics, in our formal language that we're trying to develop, remember that's our goal, our formal language that could be processed and understood by a computer that really has no idea what causality means. We want to have this formal language. We're using these propositional variables, and the idea is that we can plug any proposition we want into those, and they have a truth value, and then we should be able to assign a new truth value, right? So this is the table we have to fill out in order to define, right, what this conditional means. And we know that there are 4 possibilities, so we have 4 things that we need to figure out. Let's just think about an example before we start trying to fill out this table. Let's have 3 statements here, like 0 equals 1, 3 is bigger than 2, and I don't know, Godzilla is the king of monsters. And let's assume that that's actually true, that Godzilla is the king of monsters. So we're supposing that this is true. This one is true as well, and this one is false. If I ask you, is P and Q true, you can tell me right away that it is, right? That's true. If I ask you if P or R is true, you can tell me again right away that it is. But what about if I ask you if P implies Q is true? So this translates to, if Godzilla is the king of monsters, then 3 is bigger than 2. Certainly, Godzilla being the king of monsters has nothing to do with 3 being bigger than 2, right? But nevertheless, we have a decision to make because we need to fill in this truth table. Let's see, what about this one? How about R implies Q. So that says if 0 equals 1, then 3 is bigger than 2. How about Q implies R? So if 3 is bigger than 2, then 0 equals 1. I'm going to give you a minute to just think about which, if any, of these statements should be true.
I would like to think the first two are true and then the last one is false. Because so we have Q being true in both ends of the first two, and in the last one we have Q being true but R is false, which implies like if Q is true, that means that R has to be true as well, but it's not, so that's a false scenario. But in the scenarios where Q is true, doesn't matter if P or R are true or not, because if they are, Q is true, so it's a true statement. If P and R are false, it doesn't change what Q needs to be.
Okay, I'm going to agree with you on all that stuff. So I would claim that there is exactly one area, one row of this truth table that it really makes sense and is consistent with entailment, which is what this whole thing is supposed to model, right? We need this to be consistent with entailment as we understand it, right? And it comes down to this. If P is true, we're thinking about this arrow is saying P makes Q be true. So again, that's our idea. And in this one case where if the reality is that P is true, but Q is false, then it's not possible that P is making Q be true, right? If P is a true statement and Q is false, then P is not making Q be true, right? If 3 is bigger than 2, then 0 equals 1. It must not be the case that 3 being bigger than 2 makes 0 equal 1, right? All right, so that is really the only place in this table that that is without a doubt and without confusion got to have a false in it. Because if P is true and Q is false, then it can't be the case that P makes Q be true. We still have decisions to make about all the other statements or all the other combinations. And since they are not refuting the idea that P implies true, these are just all accepted as true. The true implies true feels good, right? Because everything's true, so it seems like the statement should evaluate to true. And these two cases, when the P part of a P implies Q statement is false, these are called vacuously true. They're basically content-free statements. Okay, so with this definition of what if then means, Yamak, am I saying your name right?
It's Yamach, but it's okay.
Oh, Yamak, okay. Let's see. With this, this definition of implication, Godzilla being king and 3 being bigger than 2, that's a true implies true. So this statement is true. This is a false implies true. It doesn't even matter what's over here, right? If the first part's false, then the whole thing's false, vacuously. So that's true. And then if 3 is greater than 2, then 0 equals 1. This is false. Even though they don't necessarily have anything to do with each other, if the first thing is true and the second thing is false, it is not the case that the first thing makes the second thing true.
I have a question.
Yes?
You mentioned content-free statement. I think that's what you said. What exactly does that mean?
Let me give names to these parts so that we can... The if part of a statement is called the antecedent, and the then part is called the consequent. Right, so So for example, if I read this second statement here, as soon as I say if 0 equals 1, I don't even need to read what the then part is. This first part is false, so it can't make anything be true. There's no relationship being asserted there. You can get very philosophical about the conditional statements and a related idea called modus ponens. But the good news is that you don't have to, and that is the whole point of the formal language, right? If you just take this truth table here, as the definition of what that arrow means, you don't need to know anything about what implication is or entailment or causality. It doesn't have to play a role in any of the analysis that you make after this. This is supposed to be something that's consistent with our reasoning, but it's really just a first swipe at trying to model human reasoning. Yeah,
Can I give an example that it helps me? First of all, we can say that all crows are black. So if something is a crow, then it is black. But just because it is not a crow doesn't mean that it doesn't need to be black. Or just because it's black, it doesn't need to be a crow. But if it is a crow, it has to be black. Like, I mean, it kind of fits in this whole thing, because like P could be the thing being a crow, and then Q is the thing being black. So if it is a crow, it is going to be black. But if the thing we're looking at is not a crow, that doesn't mean that it is not black. It can still be black. It just doesn't matter. So if P is false, if it's not a crow, it's immediately true. And if Q is true, if it is black, it doesn't matter if it's a crow or not. It's the statement would still work. I don't know, it's just how I remember it.
Let's we should start a thread of examples on Piazza about implication. Since I already mentioned contradiction, let's talk a little bit more about contradiction and something called tautologies. So some statements are always true by their very form. That is, it doesn't matter what the actual propositions are that you plug in for those propositional variables, whether it's something about it's raining outside or my shoes are red, or 0 equals 1 or 2 squared is 4. It doesn't matter what the propositional variables are when you actually plug them in. In all cases, the statement will evaluate to true. And the simplest example of that, I think, is this one. So if we make the table for this one, so this is read P or not P, it only has one propositional variable occurring in it. So we have only 2 possibilities. And if you want to break this down, you could add another column. Maybe since it's just day 2, I'll just go ahead and add that column. So not P just flips, right? Flips the sign. And so P or not P says at least one of those 2 things has to be true. Right? And when we have a statement like this, they're called tautologies. Right? So that is a tautology. This is called the law of the excluded middle. Well, assuming that this is always true, it's called the law of the excluded middle. So P or not P is true, is the law of the excluded middle. And the middle being referred to there is something that is between true and false, right? So that statement says every proposition is either true or it's false, right? There's no maybes. And we're having this statement be true because we're working in a Boolean logic that has only true and false. There are other logics that have a middle, right? That's something like you could think of it as a maybe or an undecided truth value. And there are other logics that have a continuum of truth values available. So you can think of it as having a degree of belief in something, right? If your truth value is, say, 0, then you're absolutely sure that that statement is false. If your truth value is 1, you're absolutely sure it's true. If your truth value is 0.3, then that means you have sort of 30% belief that that statement is true. these multi-valued logics are super interesting and beyond the scope of our course, but people used to talk about something called fuzzy logic. Have you ever heard that term? Yeah. That's an example of a multi-valued logic. So our logic is not fuzzy, right? Our logic that we're taking is clear, black and white, 0 and 1, true and false, Boolean. All right, so this is a basic example of a tautology. We also have this case where some statements are always false. Again, by their form, it doesn't matter what you plug into the statement variables, the statement is false no matter what. Now, this is the first most important example of what we call a contradiction. So these are called contradictions. I mean, the assertion that's being made by this statement, P and not P, is that P is true and not P is true, right? So P is true and P is false at the same time, which isn't allowed. I mean, at least it shouldn't be in Boolean logic. So we have true, false, false, true. The and means that both things have to be true, which never happens in this case. And this particular example, this P and not P, is being false all the time. Again, this is not a rule that has to be adopted. In other logics, in non-Boolean logics, you can have things like this. But this is called the law of non-contradiction. A statement should not be able to be both true and false. In other words, it shouldn't be able to contradict itself. All right, and the notation for indicating that something is a tautology or a contradiction is the following. So I would write here P or not P is true, right? And so this is just an equal sign with 3 lines instead of 2. And for this one, I would say, oops, P or, and not P is always false. It's basically saying it's equivalent to false.
Excuse me. Earlier in this session, you said that when something always is false, we call it contradiction.
Yeah, let's see here.
But then you said it's the law of non-contradiction.
Yeah, so this is the contradiction, and we're saying it's not allowed, right?
Yeah.
So we want no contradictions. So the contradictions have to all be false. Right? The false is the non. Right, so not everything is a tautology or a contradiction. There are things that are true sometimes and false sometimes. But there are statements that can be true and false at the same time. In other words, they have they come out to the same truth table. So let me show you an example. Let's do this one. So let's consider P implies Q. So we get a little more practice with implication. And the statement not P or Q. And let's build the truth tables for these two. And so I can see that these 2 columns match exactly. All right, so that means that, if you plug in the same values for P and Q in either one of these statements, you're going to get the same truth value when you evaluate that compound statement. We have notation for this. Instead of a regular equal sign, we would write that triple equal sign like we did for contradictions and tautologies. And the way that we read this is that P implies Q is logically equivalent to not P or Q. And again, this makes sense, right? Because if we think about the truth table for P implies Q, that's true if either P is false, right? So let's see, where is P false? Down here, right? Or if Q is true right here. So we should get trues for all of those, and it's false otherwise. So this is just kind of describing the rows of the truth table with T's in them for that implication, that arrow statement. So this notion of logical equivalence is what leads us to that sort of sketchy answer I put up on Piazza for the question about, is there a shorter way the truth tables are going to get big, right? And the answer is, well, yeah, sometimes. And it's because we can use logical equivalence to make substitutions and replace parts of complicated expressions with simpler expressions. Just like if you saw x plus x someplace in an algebraic expression, you might replace it with a 2x because it's simpler, it's more compact. Let's maybe do one more example of showing logical equivalence, and then I want to just give you a brief look at the algebra of propositions and some rules of logic. So here's one more example. This is an important example because it kind of tells us about the logical analog to distributing a negative, right? Like if you have minus x plus y, you know, that's equal to negative x plus negative y. This is the logical analog to that. So let's take, so this is the way I might write a problem like this. Show that negation A and B is logically equivalent to not A or not B. Okay. So we can do this by building a truth table, and we can do this, you know, mechanically without thinking about it at all, right? We write down our trues and falses and follow the rules about our definitions of and or and implies and not. But before we do that, let's just take a moment to practice reading this stuff. This says that it's not the case that A and B are both true, right? It's not the case that A and B are both true. So that is the same thing as saying at least one of them has to be false. It's not the case that they're both true. That's the same thing as saying at least one of them has to be false, right? All right, so this makes sense, right? And we can convince ourselves it's true without making a truth table. But if we really want to prove it, we want to make a truth table. So these match. So it follows that negation A and B is equivalent to negation A or negation B. So this is one of the more important logical equivalences that come up when we're doing this propositional calculus and algebra of propositions. And this has a name. It's called modus, it's not called modus ponens, it's called De Morgan's law. It's one of them, there are two. So one of them says not A and B is logically equivalent to not A or not B. And the other one says that not A or B is logically equivalent to not A and not B. This one also makes sense because it says, let's see. It says if it's not the case that at least one of them is true, that's the same thing as saying that they're both false. If it's not the case, if it's not the case that at least one is true, that's the same as saying they're both false. So this is a document that I put up. I made this a long time ago, and I just put it up for your reference. So here I was using 1 is true and 0 is false. So you might have to adjust your thinking about some of these. But let's see, So De Morgan's law is here, the two that we just looked at. The one about the conditional, P implies Q is logically equivalent to not P or Q, that is here. And all of these can be derived and derived and, and all of these can be proved equivalent just using a truth table. And none of them is too long. The longest one has these 3 letters for associativity and distributivity. Distributivity is a tricky law to use sometimes, but it's not too bad. Associativity came up in discussion on Piazza as well. It is the reason that we don't need to use parentheses when we've got the same symbol, right? So if you have ands in both of these places, then you can drop the parentheses. If you have an and an or, however, it's just like distributing. Let's see. With the understanding that you can go and read through this list carefully later, let me show you how one of these algebra things might work. So we can use equivalences to do algebra on propositions. So let's show this, not P or Q, or not P and Q. And I want to show that this is equivalent to the negation of P. Just like we could simplify an algebraic expression by using rules like x plus x equals 2x or x times x equals x squared, we can do that here too by using our laws. Like this one, I know by De Morgan's law, right, that this is equivalent to not P and not Q. And if you look at the distributive laws that are written down both in the textbook and on that sheet that I just showed you, that not P appears first in both of these, along with the arrangement of these symbols, you will see that just syntactically you can pull this out. This is one of the distribution laws kind of getting used backwards. So it's like factoring, and like factoring out that not P. And this bit, not Q or Q, we already decided that that was a tautology. So this is just true. So this is equivalent to not P and just true. This is now an and the assertion made here is that not P is true and true is true. And there's another law called identity that tells us that this is logically equivalent to not P. Right, so we've used all these rules to simplify this in a way that feels very much like simplifying algebraic expressions in an algebra class. All right, I know you guys got to go to your other class. So if you have any quick questions, I'm happy to answer them. I will annotate this with the rules that I used so that you can look them up and make sure you see how it works.